Okay, so today we're going to be taking a look at the last section in chapter 7, which is 7.5, and it is all about solving trig equations. Okay, and so this is the last section that will be on exam 3. And we'll take a look at this stuff. I've tried to chunk it into sort of like 3 different types of equations, like general types of equations, to help us keep in mind like when we might need to use what. But if you do not have your unit circle handy, I would go ahead and pull that up. Either on the interweb or from your notes, but let's go ahead and get that unit circle pulled up because we will definitely be using it today to help us answer some of these questions, okay? So I'm gonna go ahead and share my screen. All right, so 7.5. All right, so I feel like as we move on, this what we know list gets longer and longer, which is sometimes overwhelming, but hopefully more just a reminder of how far you've come since the very first day of 104, okay? So things that we know or we have learned are verifying trig identities using reciprocal, quotient, odd and even, cofunction, Pythagorean, sum and difference, half angle formulas, and algebra. Okay, so we've learned a lot of different pieces with that verifying trig identities. Now I know that's something that folks have said that is still really hard for them. I think the tough thing about verifying trig identities is it is a lot. That is the reality. And the other reality is the only way to get to that understanding is to do a bunch of them, even if you feel like you don't know what you're doing. Okay. So I would really encourage you to spend a little bit of extra time with these verifying identities. We're not really going to do that today, but in preparation for exam 3, I do think that's very important. Okay. We've also learned some more like concrete things like evaluating sum and differences of main trig functions and evaluating exact values of double and half angles. And with this, we also talked about identifying like which quadrants 2 theta and theta over 2 are in. Okay, so that would be a really important piece to make sure that you're understanding as well how to make those decisions. Okay. And yeah, you could certainly think about it like thinking about it like a language, right? You want to be really clear about what you're saying. And so being able to not just use the identities, but identify which one you're using would be really valuable. Okay. All right, so what are we adding on in this last part of the chapter? Well, we are taking a look at solving identities, okay? We're gonna start off with some basic solving equations, just like we did with like linear equations way back in the day. We're gonna do a little bit of stuff with quadratic equations, and then we're gonna use some of the identities we've learned to help us solve equations as well. And then for every problem that we do today, we're going to be finding solutions over a given interval. So over the interval 0 to 2 pi. And we're also going to find what we call general solution. Okay. And so on exam 3, you are going to have one of each type of question. They're going to be separate questions. Okay, so finding solutions from 0 to 2 pi and finding general solutions will be separate questions on the exam. But for today and for the quiz, we're going to go ahead and sort of do them both together just so we get a lot of practice in terms of how to do each one. Okay. So that being said, let's take a look at our first category of trig equations. Okay, so the first type is something called linear trigonometric equations. And what that means is we're looking at things as sort of like adding or subtracting or multiplying or dividing to find a value for x. And we're not doing anything like factoring. We're not doing anything yet like using any of the identities we've learned, okay? So let's take a look at example number 1, okay? And you'll notice that there's sort of the side for general solutions. And then there's also the side for solutions over the interval, okay? And so what we're doing here is we're really trying to say, let's find all the solutions that are one time around the unit circle. So that would be this first one, only one rotation of the unit circle. Okay. Whereas general solutions are going to allow us to find all solutions. Like no matter how many times we go around the unit circle, we'll be able to tell where we should stop, okay? All right, so let's get started with this question. So it says sine of x equals -1. So if you were to look at your unit circle, what should you look for to find the value of x that makes this true? Anybody have any ideas around that? Mm-hmm. Exactly. Okay. Where is the y value -1? We're looking for the inverse sign of -1. Those say the same thing. Okay. And so when we think about that, let's see if we can list all the places that are just one time around the unit circle that make this true. Okay. So we look at our unit circle and we say, okay, well, when x is equal to, let's see, not pi over 2, right? That would be a +1. If we go to 3 pi over 2, okay, then that's the angle that has a y value of -1. Now, does that happen any other time when we go around the unit circle just one time? No, that's actually the only time, right? There are some other angles. Actually, a lot of the other angles, things happen like more than one time around the unit circle. But in this case, for this particular y value, it only happens one time, okay? So if we just said, find the solutions over the interval 0 to 2 pi, your answer would be 3 pi over 2. Okay? Now, when we think about the general solutions, okay, what we're really saying is we can go around the unit circle an infinite amount of times, okay? And so if I were to kind of draw a picture that goes with that, right, here's my unit circle. Well, not bad for a Monday morning. We know that our solution is right there, right? Yeah. So when we're answering all these questions, we're assuming that we have the unit circle, okay? And so that's why the largest value that sine or cosine could be is 1. Okay. All right, so when we have this, if I went one time around the unit circle, I would get to here and I would stop. That would be my solution. But I could think way back to that first unit that we did where we talked about we can go around the unit circle more than one time. And so if I went around another time, I would want to stop at the same place again. That would give me another solution, okay? And I could go around that unit circle as many times as I want, but I would have to stop every time I got to the yellow dot, okay? the way we write that, because we don't want to sit and list out every single solution, is we say, here's our one solution, okay? And it's not multiples of 3 pi over 2, okay? But we're saying we want to think about plus every time around the unit circle. Like, that's what we're doing in words. We're saying 3 pi over 2 and then every time around the unit circle, okay? In terms of radians, how big is one time around the unit circle? Yeah, it's 2 pi, okay? So if I wrote this, x equals 3 pi over 2 plus 2 pi, well, that would give me, if I went around the circle one more time, right? How would I say it if I wanted to go around the circle 2 more times? Yeah, I could say 4 pi, right? 4 pi would mean I went around the circle 2 times. What about 3 times around the circle? It would be 6 pi, exactly. What about if I said we're going one time around the circle, but in the opposite direction? How would I say that? Negative 2 pi. Good, very, very good. Okay, so everything that you've told me, and here's where the multiples come in. Everything you've told me is a multiple of 2 pi. So the way we write that is we say 2 pi and we add a, or not add, we multiply a k there as well, okay? So the k is what tells us how many times around the unit circle, okay? So every time I put in a number for k, that tells me a different solution. So I could have k as 1, that would be like I go around 1 extra time. I could say k is 2. I go around 2 times the circle. I could say k is -1. That would mean that negative 2 pi in the other direction that you folks just said, okay? So the concept, you guys have the concept. We're just layering on this new notation, okay? So we're going to say x equals the solution that you have. So this is our solution. And then this is rotations around the unit circle. Okay. Now I'm going to add one extra piece here, all right, which is that k is, and we're going to write an E that looks like a half circle with a line. Okay, let me write that again. So it's like a half circle with a line. Okay, a half circle with a line. A half circle with a line. Right? And that symbol just means that something is an element of. Well, when we want to go full rotations around the unit circle, that means we could only use whole numbers for k. So like 1, 2, 3, 4, -1, -2, -3, -4, okay? And the way that we say integers is we write a z, and it's usually script, so I just put like a second line like I do with the all real numbers are, and then I usually write a bar through my z. But this z means integers, okay? So take a moment real quick and kind of practice writing that. Like, what does your script Z look like? How do you write this half moon thing with the line in it that says is an element of, okay? But this part right here is the part that guarantees that we're doing full rotations around the unit circle, like 2 pi. We're not doing a half a rotation, we're doing a full rotation, okay? Okay. Any questions so far, whether it be on notation or how we got this answer again? Okay, so let's try a second question, okay? So last time, Thea was so kind to translate the sine x equals -1 for us. Well, hold on, there's a question. So if it doesn't have k as an element of z, it's a half rotation? No, if you don't write it, in theory, you could put anything in for k. It could be like the square root of 2. That's like a weird rotation. It might not even be a perfect rotation. Okay. Yeah. And it's more like if you're going to introduce a new letter, then mathematically you kind of have to define what it is. All right. So if you introduce a new variable, you kind of have to tell whoever's reading your work what that stands for. Mhm. Yeah, Ethan, that's a great way to summarize it. It basically says that k is a whole number. You're either going 2 pi, 4 pi, 6 pi, 8 pi, could be 0 pi, right? 0 pi, -2 pi, -4 pi, -6 pi. And we will take a look at some in a little bit, Christina, that where we only go around halfway around, and we'll talk about how that changes when we write our notation, okay? Okay. All right, so if we were to translate this question the same way that Thea translated sine x equals -1, what could we say we're looking for when it says cosine x equals 1/2? What does cosine x equal 1/2 mean we're looking for on that unit circle? Exactly, we're looking for where the x value is 1/2. Exactly, perfect. Where does x equal 1/2? And so let's look at our unit circle and see if we can find where does x equal 1/2. All right, so I agree we've got a pi over 3. So we could say that this at pi over 3 definitely has an x value of 1/2. So x equals pi over 3. And perfect, Michelle, 5 pi over 3. And 5 pi over 3 is actually down here, right? So 5 pi over 3 is the other place where it has an x value of 1/2, okay? So if I said find the solutions over the interval 0 to 2 pi, okay? You would say pi over 3 and 5 pi over 3. And so that's very similar to what we learned in the very first unit when we were just learning how to find the unit circle values, right? Okay. So if we think about the general solutions, now we need to think about, okay, how do I incorporate this idea of multiple times around the unit circle for the solutions, okay? Now, if I think about the pi over 3, if I were to go around one more time, I could land at the same pink line. If I went around 2 more times, I could land at that same pink line, okay? And so the way I say that is x equals pi over 3 plus as many full rotations of the unit circle that I want. And I'm defining k to be an element of the integers. Okay. And what I just wrote would get me all of the solutions that match that pink line from my set of solutions between 0 and 2 pi. Okay. To get the solutions at the green line, what would I change about that statement? Start at the green line plus as many rotations around the unit circle as I want. But we need to make sure that they are full rotations around the unit circle. Okay. All right. Let me just squeeze example 1 and 2 on the same page here. Whoa. How are we feeling about those so far? Okay. David, what do you mean by minus? Can you clarify that statement for us? Well, here's the thing. K can be any integer. So K could be +1, but it could also be -1. K could be +2 or it could be -2. So in general, when we write formulas like this, we typically write a plus so that the minus sign can get built in.
I have a question.
Sure.
Or I guess we're gonna find this out in a second, but 0 to 2 pi, that range, so 0 is included, but it's up to 0, so it can't be like a negative number, right? Because, or
Correct. So if we're asking for solutions over the interval 0 to 2 pi, we're really saying your answer needs to be a number between 0 and 360. So no negative angles.
oh, I see. The other one's just general solutions. Okay.
Yeah, so the general solutions is like, how many other ways can we name that angle? We could call it 7 pi over 3. We could call it -5 pi over 3. Like there's so many ways to name that particular angle. It just depends on how many times we go around the unit circle. So that's why those could be negative. Okay. So we separate our general solutions. We would never list them on one line followed by the notation. Oh, you mean like the k is an element of the integers part? I think that sometimes folks do, right? Like x equals, might write like x equals pi over 3 plus 2 pi k, or 5 pi over 3 plus 2 pi k, and then define the k at the end. Like I think that way might be a little bit too condensed, because we're looking at like one solution that like comes from one of the answers and then sort of a second one. But yeah. Okay. But I think one thing that I'm trying to sort of highlight here is maybe some notation you'll see, depending on how far up you move in the math world, to think about like how we typically write things. But whatever it is, let's just make sure that we know, like, we're clear on what we're looking for. Okay. All right. Any other questions so far? Would negative pi over 3 minus 2 pi k be a viable general solution? Yeah, it would be, because that would be another way of writing the thing you have in the green. Right? Because 5 pi over 3, another name for that is negative pi over 3. But I think what is sort of important to recognize is if we're looking for solutions from 0 to 2 pi, like this pi over 3, it makes it easy for us to find the general solution. And then this calling this 5 pi over 3 is the only way to answer the first question. But when you get to here, in theory, you could call it whatever you wanted to call it in the general solution. Yeah, exactly. So it's almost like we're trying to set ourselves up to do as little work as possible to write the general solution, is really where we're going. Okay. Yeah, so negative pi over 3 would be okay for the general solution, but if someone says, I need you to give me answers between 0 and 2 pi, you want to make sure your answers do fit in that range, right? What do you mean by same distance? Mm-hmm. Exactly. If we have two solutions that were exactly halfway around the unit circle from each other, then we could find some shortcuts for that, for sure. Okay, so sounds like we're ready to move on. So let's take a look at example number 3, okay? So for example number 3, this still falls under the category of linear trigonometric equation. So what might we need to do in order to isolate my cosine? Because in example 1 and 2, we had the cosine or we had the sine all by itself. So how do we get this all by itself? Plus 3 on both sides. Okay, so 2 cosine x equals negative 5 plus 3 is negative 2. Okay. And then dividing by 2 on both sides, good. So cosine x equals negative 1. Okay. Does that part make sense to folks? In terms of how we isolate that? Okay. Yeah, so we're just trying to get that trig function all by itself, okay? So we get cosine x equals negative 1. So now let's take a look at our unit circle. And where does cosine x equal negative 1? Yeah, exactly. That is exactly what we're doing. Okay, so where do we see cosine of x equals -1? At pi, good. So we could say x equals pi. And are there any other locations where this is true? At least in the interval 0 to 2 pi. No, right? This is our only solution. And so in this case, we have one solution for the interval from 0 to 2 pi. And so when we think about our general solution, we can say we're going to start at pi and we're going to count around the unit circle however many times we want in whatever direction we want, because k could be positive or k could be negative, as long as we define k to be an integer. Okay. So not so bad, right? We're sort of dressing up the stuff that we've seen before and doing it in sort of combining a lot of things that we've learned in the past, like how do you solve a linear equation and how do we combine that with what we know about the unit circle? Okay, well, let's move on to example 4. Okay, so cosecant here, right? What is this question really asking us? Cosecant x equals -2. What is that asking us? Yeah, this is asking us for the 1 over y value to be -2, right? We're finding an angle where the 1 over y value, because sine is y, so 1 over y is equal to -2, okay? Now, I know that a lot of us out there, and myself included, are just not as comfortable working with cosecant or secant. So here's a little trick that I think might be helpful in terms of making sure you know what you're looking for on the unit circle. So once I have my cosecant by itself, here's what I typically do. I know that cosecant is the reciprocal of sine, right? And that's -2 over 1. So here's the deal. Because I have an equation where things are, it's a fraction equals a fraction, I can flip both sides. And I think this is what Natalia was sharing in the chat, that instead of writing 1 over sine x, which is like weird for our brains, let's write it as sine x. So we took the reciprocal of the left side equals -1/2. That's the reciprocal of the other side. Okay. Now this is a question that I feel confident that we can all remember. Or not remember, but we all feel comfortable with, right? So if the cosecant freaks you out a little bit, write it like a sine. If the secant freaks you out a little bit, write it like the cosine, okay? So as long as you take the reciprocal on both sides, you're good to go, okay? So then the question is really, which angles have a y value of -1/2, right? So let me draw a unit circle real quick. All right, somebody got in. Oh, all right, totally got it. 7 pi over 6. All right, so we've got this as our 7 pi over 6, and the other one is 11 pi over 6. Okay, and both of those have a y value of -1/2. Okay, now Ethan actually asked a really important question earlier. So this pink line and the green line, are they exactly halfway around the unit circle from each other? No, they're not, right? They're not like 180 degrees apart. They're like a little bit closer together, right? Or a little bit further, depending on which way you count. So because they're not exactly halfway around, when we write our general solutions, we got to write the first one plus rotations around the unit circle. Okay, so this one would correspond to that general solutions for the pink angle. And then this one, 11 pi over 6 plus 2 pi k, where k is an element of the integer. That would show all of the general solutions for the green angle, okay? Now we are going to see some, actually, I think in the next problem, where we're going to be able to combine maybe two answers into one answer. And I know that there's a lot of us out there who prefer to write less than we have to. So this, I think, will be a good place where we can kind of think about when we can shortcut things and when we can't, okay? Are there any questions about the cosecant one before we move on? All right, let's take a look at example 5. What's your thought process? If the y value is 2, then it should be a 1 in the numerator. If the y value is 2, but the 1 over y value is 2. Okay, so I think if you sort of walk yourself through this process, like if you kind of flip both sides, then you are looking for the y value. Does that make sense? Okay. This applies to other functions too, like we can take the reciprocal. Yeah, so let's say, for example, I gave you a question that was like secant x equals 2 over root 3. Okay, and I think, again, sometimes people panic when they see secant. They're like, oh, I don't know, I just didn't learn that. But let's think about what we know, the reciprocal, right? So the reciprocal of secant is cosine. And what's the reciprocal of 2 over root 3? Yeah, secant is 1 over cosine x, yeah. Okay, and so when we take the reciprocal of 1 over cosine, we also have to take the reciprocal of the other side. Exactly, that's where you get the root 3 over 2. Now, isn't this much easier to find on the unit circle, right? We're just looking for an x value that has, or an angle that has an x value of root 3 over 2. Okay, so yeah, this here in the blue, as long as, in addition to sort of what we talked about in example 4, that's exactly how you can handle it when it comes to reciprocals, okay? Yay, okay, good. All right, so example 5, okay? Now I feel like tangent also makes people a little nervous too, right? Sine and cosine, we know that's our y value, we know it's our x value. And tangent, well, I think we learned in the last 2 chapters that, like, we really need to be confident with our dividing fractions. There's a lot of like root 3s and things like that. So I didn't actually use those values in this question, but exactly, in this case, we're looking at where does tangent equal 1, okay? And so what I want us to think about is, where does, like, what angle does tangent equal 1? Okay, I think for this one, there should be more than one answer when we go one time around the unit circle. exactly, at pi over 4, because the y and the x value are the same, right? They're both root 2 over 2. And when they're both root 2 over 2, but they're negative, okay? So pi over 4 and 5 pi over 4 are the angles where the y over x equals 1, okay? Now, let's go back to our question for a moment, because what I did is I actually made a very sneaky substitution here. And my substitution was I thought about it in terms of theta. And really, theta is the same as x minus pi, okay? Do people need more clarification around where these came from, or are we okay? Okay, so when we think about theta, right, when we look at the y values, we want to think which angle has a y divided by an x that gives me 1. Yes, Richard, that's what we're going to do, exactly. Okay, so in this case, if I want to get two things divided and it equals 1, well, then the x value must equal the y value, right? They have to be the same. And so when you look at the unit circle, you want to look for where are the coordinates the same, like exactly the same. Like the y has to equal the x, including the sign, like positive and negative. And so when you do that, you'll find it's pi over 4 and 5 pi over 4. Does that clarify the tangent part for you? If that's not clear, I would definitely stop by office hours. Okay, I would stop by office hours because I'm happy to explain that tangent part a little bit more. Why does theta equal x minus pi over 2? Because when I think about the way I answered this question, I said tangent of some angle equals 1. But the angle is x minus pi over 2. Okay. Vianney, you're saying there's not parentheses around the x minus 3. Yeah, there's actually a really big reason why it doesn't have parentheses around x minus 3. This is an entirely different question. Because the second one is saying you would be looking for, what's that use red? Cosine of some angle equals negative 5 over 2. That's what you would be looking for. Okay, so those parentheses definitely play a big role there. Yeah. Okay. If folks are still confused about the angle stuff, like how do you find tangent and some of the other ones, I would definitely recommend coming to office hours. But for right now, we are going to move on, okay? So when we're looking for these solutions over the interval 0 to 2 pi, what we're saying is we know that the thing in the orange has to equal pi over 4. That's one possibility, right? Because we said pi over 4 was one solution. Or the other one is the thing in the orange, or that angle, whatever we want to call it, is equal to 5 pi over 4, okay? So we sort of have these two pieces here. Now, because of the parentheses, and Vianney, I'm really glad you highlighted this, because of those parentheses, it does mean that we need to do a little bit of work to get the x by itself, right? Because now we don't have x yet, we have to add pi over 2 to both sides to find our x value, okay? And so when we add pi over 2, we're going to get pi over 4 plus pi over 2, okay? And if we change things to common denominators, we get pi over 4 plus 2 pi over 4, or we get x equals 3 pi over 4. Okay? So that is the first solution. The second one, well, we're going to do the same thing, except instead of taking pi over 4 and adding pi over 2, we're going to get 5 pi over 4, and we add pi over 2. And so that's going to give us 5 pi over 4 plus 2 pi over 4, which should give us 7 pi over 4. Okay. So those are our two solutions, but I do want to take the time to draw a little unit circle and mark these off so we can kind of see what we're looking at, okay? So what we're saying is that if we take our solutions and we mark them on the unit circle, we'll get one solution that's here. This is our 3 pi over 4, okay? The other solution is the 7 pi over 4. Now, for question 4, I said, are the pink and the green angles exactly halfway around the unit circle from each other? And we said no, right? That's why we had to write them separately. But when we look at what we have for example 5, well, we could go around the unit circle multiple times to get the pink one. We could go around the unit circle multiple times to find the green one. But that requires us to write two separate equations. Okay. What we could do instead is we could do this. We could say, let's go to the 3 pi over 4. And instead of going all the way around the unit circle, instead of going around 2 pi, let's do like Natalia said, we're only going to go around 1 pi. Now, if I go 1 pi, guess where I land? I land at the green angle, which is good because that's one of the solutions. What if I go another half pi or another half rotation around? That gets me back to the pink angle, right? What if I add another pi to the pink angle? Where do I get to? I get back to the green, okay? So this is a very special case here. The special case is that when you think about your solutions, they are exactly halfway around the unit circle from each other. And so what we're able to do in this case, so because the solutions are halfway around the unit circle from each other, okay, we can collapse two solutions into one, meaning this. We can say x equals 3 pi over 4 plus, instead of 2 pi k, we say pi k. The pi k means we're going to stop every half rotation around the circle. Okay, so Christina, this is what you were asking about earlier. You said, like, how do we write it if it's a half rotation? We leave out the 2. We say we're going to stop every pi, and every pi is halfway around the circle. Okay, so 3 pi over 4 plus pi k, and k is still going to be an integer, and this means a half rotation around the unit circle. All right. I'm so glad you asked that question earlier. Right, exactly, Natalia. No matter what the number is for k, your output will always be a solution on the unit circle. Exactly. We're not getting wider, we're just counting extra times around that circle, okay? So if anybody's ever run track and you've ever done, or cross country, or you've ever done, you know, a race on a track, right? No matter how many times, if you go around one time, you're gonna end up where you started. That's kind of the same idea we're looking at here, okay? All right. So this actually seems like a good place to take a break right now, okay? Because the next two questions are going to get a little meatier into how we find solutions, all right? And so let's see, it is 10:35 right now. Let's be back at 10:45, and then we will pick up where we left off, okay? All right, see you folks back here in a little bit. Recording. I'm going to share the screen. Sorry. Okay, so let's take a look at example number 6. Okay, so example 6 and example 7 are still what we consider linear trigonometric functions. Okay, but what's different about 6 and 7 is sort of the same thing that was different about number 5. Okay, so back to Vianney's question about like why there were parentheses around the x minus pi over 2, because that x minus pi over 2 is the whole angle that we're trying to figure out information about. Okay, so just like we highlighted the x minus pi over 2, in example 6, we are going to highlight the 3 theta. Okay, so that whole thing is quote unquote the solution that we're looking for. And if we were to scroll down to number 7, what should we highlight in number 7? Yeah, that 2 theta, right? The 2 theta is really going to be what makes this question different than questions 1 through 4, okay? So let's start with example 6. If we were to think first about isolating this sine 3 theta, then what we'll do is we're going to go ahead and subtract the root 2. So I'm going to get 2 sine of 3 theta equals negative root 2, because all I did was subtract it, okay? And then what we're going to do is we're going to divide both sides by 2. So we get sine of 3 theta equals negative root 2 over 2, okay? And Edward, you're right. We're actually going to be able to solve number 7 without the double angle. So sometimes you can. And then we're going to see an example later on where it might be more helpful to use the double angle identity. Okay. All right. So with this particular question, can someone tell me where one location where 3 theta could possibly be? Like, where is one location where the y value equals negative pi over, or negative root 2 over 2? 5 pi over 4, I agree. And there's one more location where the y value is negative root 2 over 2. And yes, folks, that would be 7 pi over 4. Okay? Okay. So normally we've solved everything and then we have found our general solution. Okay? For these kinds of problems, 6 and 7, I actually find it helpful if we find the general solutions first, okay? But let me kind of tell you why that is. So when I think about this first one, 3 theta equals 5 pi over 4, how am I going to get theta by itself? Yeah, I divide by 3. So I get theta equals 5 pi over 12. Does that make sense how I got 12 in the denominator there? Yeah. Okay, so I just divided both sides by 3, okay? Now, similarly, I could solve the second one the same way. I divide by 3, I'll get 7 pi over 12, okay? So these ones, before we go ahead and say, all right, those are our two solutions, that's it, we need to make sure that we get all the solutions from 0 to 2 pi, okay? And so what we have here is some of the solutions, but not all of the solutions. So what we need to do is sort of use what we know about the general solutions to help us figure out where all the other solutions are, okay? So I'm going to go back for a moment and just copy down 3 theta equals 5 pi over 4, okay? But as a general solution, I would have written plus 2 pi k, right? Okay, now let's divide everything by 3, okay? So when we divide everything by 3 now, we get theta equals 5 pi over 12 plus, well, you got to divide that 2 pi k by 3 as well. You have to divide both parts by 3. So when we divide that second part by 3, we get 2 pi over 3k. All right, so all I've done so far is divide 3 to both sides. Okay. Now this next part is optional, okay? But before you stop listening because I said optional, I think that it's actually pretty helpful to get back to those solutions between 0 and 2 pi, okay? So what I like to do is I like to take this one step further, 5 pi over 12 plus, if I make this second denominator 12, what's my numerator for the second fraction? In other words, if I were to make a common denominator, 12 and 12, yeah, we would get 8 pi, okay? This part is helpful in finding solutions from 0 to 2 pi, okay? Because remember, we want to get all the solutions between 0 and 2 pi, okay? If we want to get all the solutions, we have to keep adding 8 pi over 12 until we get to 2 pi. all right? Now let's think about 2 pi. If I were to write this as 0 pi over 12, how could I write 2 pi as something over 12? Okay, so we're just trying to find a common denominator here. Yeah, I could write that as 24 pi over 12, okay? Now, why would we unreduce the fraction? Well, we can unreduce the fraction so we kind of know when to stop adding 8 pi over 12, okay? So if I add 8 pi over 12 to 5 pi over 12, what do I get? If I take my solution, I add, yeah, I get 13 pi over 12. Okay, is 13 pi over 12 still less than 24 pi over 12? Yes, okay. So that means it's still a solution in my interval of 1 time around the unit circle. Okay. Well, let's add it one more time and let's see. If I add it one more time, what do we get? So I'm taking the 13 pi over 12 and I'm going to add 8 pi over 12 one more time. I get 21 pi over 12. Good. Okay. Any folks in here play blackjack? Okay. We are adding, let's go back to that question first because I think that's important. Why are we adding 8 pi over 12? Because our solution says that we start at 5 pi over 12 and then we add 2 pi over 3. We add multiples of 2 pi over 3. But I know that when I add fractions, I need a common denominator. That's why we unreduced it and changed it to 8 pi over 12, right? Easier to add. But the when to stop part, that's this part. I have to stop before I get to 24 pi over 12.
So just to make sure I'm understanding this right, basically we're adding 8 pi over 12 to get as close as we can to 2 pi over, or 24 pi over 12 to see how many times we can go around the unit circle, sort of.
Yes, the thing is,
Okay.
because we were looking for 3 theta, that's where we get the full rotation, okay? Sometimes, though, we don't go a full rotation to find another solution. Well, how far around the circle do we go? We go 2 pi divided by 3. That's our new rotation for this particular question because we have 3 theta, not theta. Okay. Now, of course. So when we kind of go back to the earlier line of thought, I was saying like, how many of you have played blackjack? So if you ever played blackjack, you have 2 cards at a time, right? And your goal is to, well, you start with 2 cards and your goal is to get as close to 21 as possible, right? But what happens if you get 22? Like you add up your cards and you get 22, you lose, right? You lose if you go over 21. So you could have to get as close to 21 as possible, but not go over. So that's kind of the same thinking when we're saying here, I want to get all the solutions from 0 to 24 pi over 12, okay? But I don't want to go over 24 pi over 12 because then I've gone more than one rotation around the unit circle. So when I think about the solutions I have so far, I've got 5 pi over 12, 13 pi over 12, and 21 pi over 12. Because check this out, if I add 8 pi over 12 one more time, I get a number that is more than 24 pi over 12. So that's like when you get 22 in blackjack. Sucks because you went over, so you lost, okay? So we want to get as close, we want to get everything that is up until 24 pi over 12, but not after it for the solutions between 0 and 2 pi, okay? Why is it 24 pi over 12? Because we only want to go up to 2 pi. Well, what is 2 pi as a fraction over 12? It's 24 pi over 12. Cool. Okay. So it's really important that we sort of understand that reasoning, because in order to finish answering the question, we need to do the same thing again, but for the other solution, okay? So if you didn't get it the first time we went through it, let's sort of clear our minds a little bit and let's try this again, okay? So the second solution I'm looking at is 3 theta equals 7 pi over 4 plus 2 pi k, right? But I don't want 3 theta, I want 1 theta. So how do I achieve that? How do I get this to say theta equals and not 3 theta equals? Yeah, we're going to divide by 3. Okay, so when we divide by 3, we're going to get 7 pi over 12 plus 2 pi over 3. Okay, perfect. Now, again, this next part is optional, but I know that adding fractions means I need to have a common denominator. So I kind of like to take care of that right when I'm here. So plus 8 pi over 12. Okay. The benefit to writing this is now all I've done is I've just made a common denominator. So it makes all my work for the specific solutions a little bit easier, okay? All right, so 7 pi over 12 is one of these solutions. But to find another one, where did I get 8 pi over 12? I found a common denominator. 2 pi over 3 with a denominator of 12 is 8 pi over 12. Like you multiply the top and bottom by 4. Right? 3 times 4 gives you 12. How would you add these? Because if you wrote this, that would be real wrong. Right? How do you add those? Yeah, so we're going to keep the 7 pi as over 12, but then we have times 4, so we get 8 pi, and on the bottom we do times 4, so we get 12. All right. And that's all we're doing. We're just trying to find that common denominator so that we can add. Okay. Now we want the common denominator because we are going to add. We have 7 pi over 12. We're going to add 8 pi over 12 to see if there are any more solutions inside that unit circle. So if we get 8 pi over 12, we add it to that 7 pi, we'll get 15 pi over 12. Okay, so 15 pi over 12 also works. All right, what do we think? We want to try adding 8 pi over 12 again. Do we think we can fit it one more time before we lose? I don't know, let's try. All right, so 15 pi over 12 plus 8 pi over 12 gives us, ooh, we're real close, but we just made it. We were able to squeeze in one more solution there. Okay. We want to stop here though, right? We want to stop because we know we're close to that blackjack. Like we're close to 24 over pi or 24 pi over 12. So since we're so close, we're going to stop. And all 3 of the green ones and all 3 of the pink ones are solutions from 0 to 2 pi. Okay. Let me sort of zoom in a little bit so we can take a look at that. And let's just see if there are any questions that come up before we try this one more time, okay? All right. So here's what we're going to do. We're not going to go into breakout rooms, but I'd like us to take a look at example number 7 over here, okay? And what I'd like you to do is write down a few things, like throw a few things into the chat about what you think we should do, whether it be to start approaching this problem or things that we should be careful of. I know last time we changed the 2 pi to 24 pi over 12. Is that going to be the same or is it going to be different? Okay, so let's take a moment and just kind of start to work through this and think about what's going to stay the same, but what's going to change about our approach to number 7. Yeah, add root 3 over 2, then divide by that 2. All right, I love that. I love that. Okay, so let's get started there. Cosine of 2 theta equals root 3 over 2. Okay, this is good. All right. What I like about the intuition to do this is now you're making it look as similar to 1 through 4 as possible. Okay, you're bringing it back to a simpler version. Right. All right, so once we've isolated that cosine, what do we do? Or what are some things that we have to do to take care of our solution? Well, I bet you guys can tell me what 2 theta equals. I buy that. Pi over 6 for sure is one of those. Yeah, we're just using our unit circle here, right? 11 pi over 6 and pi over 6. So let's kind of pause here for a moment. All right, are we okay with how we got 11 pi over 6 and pi over 6? Okay. So what we're really looking for, maybe you could replace it. If I just asked you this, cosine of x equals √3 over 2, what would your answer be for x? Okay, so this kind of goes back to like that first unit where I was like, I want you to write these sentences out. And I'm sure some of you were like, I don't need to write these sentences out. I get it. But it kind of keeps coming back, right? So when we're looking at this, cosine of x equals √3 over 2, exactly. What angles have that x value? Well, pi over 6 and 11 pi over 6. Okay. So all we're saying is that instead of an x, we happen to have a 2 theta there. But if x equals pi over 6 and 11 pi over 6, then 2 theta equals x pi over 6 and 11 pi over 6. Okay. Good. That's an important thing to get. Okay. Want to make sure that's clear before we leave today. All right. Now we could, at this point, find some of the solutions. Okay. Like we could write theta equals, let's divide by 2, so pi over 12, or theta could be 11 pi over 12, right? All I did was divide by the 2. But if you stopped there, that would be a bad thing because you didn't get all the solutions from 0 to 2 pi. You got some of them, right? And we want to make sure we can get all of the solutions. So how do we make sure we get all the solutions? Well, when I divide by 2, it's the same as multiplying by 1/2. Right? So pi times 1 gets you pi, and 6 times 2 gets you 12. Yes, exactly. You get more pieces, or you could even think about it like you made the pieces smaller, right? And so when you have, if I give you a 1/6 of a pie versus a 1/12 of a pie, if you're hungrier, you probably want the 1/6 of a pie. You want something a little bit bigger, right? Wouldn't we all? Wouldn't we all? Okay. So back to our question, how do we figure out how many other solutions we have going one time around the unit circle, right? How do we figure that out? Maybe let's take a look back at what we did up here. How did we get 13 pi over 12 and 21 pi over 12 and 15 pi over 12 and 23 pi over 12? Like, how did we get those? Okay, we didn't add 2 pi though. If we wanted to add 2 pi, we would have done this plus 24 pi over 12, right? That would be adding 2 pi. But yeah, that's where we need to go back to that general solutions, okay? We need to go back to the general solutions because we're adding the equivalent of 2 pi if we're counting by threes, which is 2 pi over 3, okay? So you're going to go back, take what you have, all right? Take what you have, and I recommend starting from the 2 pi part. So 2 pi equals, 2 theta equals pi over 6 plus 2 pi k, all right? Now let's divide everything by 2. What do I get when I divide 2 pi k by 2? I'm just going to get 1 pi. I'm not going to get pi over 2. Taking 2 pi and I'm dividing it by 2. Okay, so I'm going to get pi k. Okay, now I'm thinking ahead here. I know, I kind of secretly wanted to try those, you know how they have the turducken where they put like the chicken inside the duck inside the turkey? Anybody heard of that? Yeah, yeah, I don't know. I don't know that I'd actually want to eat that. I think it's just bored people. I don't know. But anyway, I've seen something where they make like a pumpkin pie and an apple pie and maybe like a cheesecake or something. It's like 3 layers wrapped inside of a pie or something, like a cake pie sort of situation. Yeah. So that's what reminded me when you said the pie cake thing. But we're dividing by 2, so we get pi k, not pie cake. All right. But if we sort of think ahead, like this is totally fine to leave as an answer. Like you can have this as an answer for the general solution. But knowing that we have to think about adding something to the pi over 12, okay, well, maybe we should prepare by thinking about what we're doing and find that common denominator, right? So I have pi over 12 plus, how do I write pi as a fraction with a denominator of 12? Yeah, so we get 12 pi over 12, right? And this is sort of that optional piece that actually prepares you super well for thinking about how we take this and what do we add to it, because it's not always 8 pi over 12. If it was always 8 pi over 12, I would have given you a formula and been like, always add 8 pi over 12, right? But how come last time we added 8 pi over 12 and this time we're adding 12 pi over 12? Because I think that's really the understanding here. Why is it sometimes one number and other times another number? Depends on how many thetas you have. All right, yeah, that's exactly it. If we go back to this first one, right? we divided by 3. So we took 2 pi and we divided that by 3. That's how we got 2 pi over 3. And 2 pi over 3 is where the 8 pi over 12 comes from. Okay. This time, though, we're dividing by 2. So when we divide by 2, we get pi, not 2 pi over 3, right? So the thing you're dividing by changes this part, which then changes what you need to add every time. Okay. Let that simmer in your brain for a second. I know that's kind of a lot, but the idea here is we need to think about that coefficient, because that coefficient will tell us what we need to add, okay? Exactly. So now we add 12 pi over 12 in order to find all the solutions. Now, how do we know when to stop? What is sort of our blackjack 21 here? Like, what's the number that we're going to stop at? Okay. And how did you get that? Yeah, we thought about where that, another way of saying 2 pi with the correct denominator is 24 pi over 12. Okay, so we want to stop when our numerator gets close to 24, but we don't want to go over or we're going to lose. Okay, so we're going to add 12 pi over 12. We'll get theta equals 13 pi over 12. Think we can add again, or are we going to go over? Yeah, if we add one more time, what are we going to get? 25 pi over 12? Yeah, that's too big. Okay, so this time we get 2 solutions from that one solution. Okay. All right, so let's go back to that other solution then. We had 2 theta equals 11 pi over 6 plus 2 pi k, right? Well, we got to take care of that coefficient. So we got to divide, but we got to divide everything by that coefficient. So theta equals 11 pi over 12 plus pi k, or to prepare, 11 pi over 12 plus 12 pi over 12 k. So this, we could say, is our second general solution. And in order to find all of the solutions, one rotation around the unit circle, let's add. We get theta equals 23 pi over 12. That's so close to 24 pi over 12, I kind of know I don't need to try another one, right? That's like getting 20 in your cards. You're probably pretty good to go unless you think you're going to get an ace next time, right? And Thea, that's a good point. We should be making sure that we note that k is an integer for these. Okay. Let's go back. K is an integer. Integer. Okay. All right. So, did that second example make a little bit more sense than the first one? Or are we all still feeling kind of lost with this? I think that's a great question to ask yourself. I think you have a couple of questions like that to try on the quiz, so that might be a good thing to check out and see. Because of that interval, we can't pass 24 pi over 12. Yeah. Okay. All right. So definitely come back and maybe annotate this section of your notes a little bit more. I think it's definitely a tricky thing because we're sort of going back and forth between the different solutions, all right? But go back, spend a little bit more time on this, and then I feel like questions 1 through 4 are going to seem so easy in comparison, okay? All right, so our favorite, we are bringing back the quadratic, okay? So with the quadratic, the important thing we are looking for here is sharpening our skills on factoring, okay? So we are sharpening these skills because I don't think I've ever taken a math class where I don't need to factor, okay? So we want to make sure that's a skill that we have, and we want to make sure it's something that we feel confident in, all right? So let's get started. Let's take a look at example 8, okay? Now there's sort of one thing that I've been telling you as we sort of approach quadratics in order to solve them. What is that thing when I'm like, you see the squared, I want you to do something, and there's something I want you to do every time you see a squared in your equation. No, I don't want you to distribute. I do want you to factor it, but before you even factor, there's something you have to do. Like, what if I gave you this? What would you do? Better not take the square root. Set it equal to 0. Okay, so you see the quadratic, and I'm like, all right, you got to move everything to one side. You have to set it equal to 0. Okay, so when we see something like this, our first instinct should be move everything to one side, set it equal to 0. Okay, so anytime we see something quadratic, that's the route I'd like us to take. Okay, so let's take a look at this example. I look at this, I see the sign, and I see the squared, and we are not jumping too many steps here. So I want to make a few things really clear, okay? So if I see the squared, automatically I'm thinking, take everything, move it to one side, set it equal to 0, okay? Please, 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 please do this, okay? 2 sine squared x plus sine x equals 0. Okay. We want to remember sine squared x is the same thing as sine x squared. Nobody writes it like that, but we want to know those are equivalent. Okay. So when we take a look at this side, once we've moved everything to one side, then we have some options. Then we can say, hey, do we want to factor? Sometimes we need to factor. Do we want to look for a greatest common factor? Sometimes we look for a greatest common factor, okay? So it really depends on what we are thinking about is the most efficient strategy, okay? And in this case, we happen to have a greatest common factor, okay? Now here is the important part. The reason why I want us to move everything to one side, set it equal to 0, is because of this. Let's say I have something times something else, and it equals 0. What number could A be? 0, okay. What number could B be? 0, okay. And that's true. If A is 0, then B can be anything, right? It doesn't matter as long as A is 0. And we could also flip that, because if B is 0, then A could be anything, right? But let me ask you a separate question. A times B equals 1. What could A equal? Give me some possible values for A and B that make this true. Okay, A could be B, which could be 1. That's valid. Okay, what else? What else could A and B be equal to? I love it. A could equal B, which could be -1, right? Okay, what else? Okay, you could have A equals 1/2, B equals 2. That would work. I love it. What else? You gonna make me write out all those numbers? Yep, 1/4 times 1/4. That really long number that Natalia typed in there, right? But the bottom line is this. If you have two things multiplied and it equals a number, you can have an infinite number of solutions. So many choices. But what makes this so special? One of them has to be 0. Right? That's the only way this is going to work. One of them or both of them have to be 0. I know you guys know this, but that's why it's so important when we factor, that before we factor, we move everything to one side and we set it equal to 0. Because if we don't set it equal to 0, we can't really say what each part equals anymore, okay? So it's that piece that's so crucial. Two things before you factor. If you factor, they have to equal 0 so that you can get some solution. Okay, good, excellent. Well, I should have just called on you to do that then. Okay, but from here, here's what we get, right? We get sine x could equal 0. That's like my A that we just talked about. Or 2 sine x plus 1 equals 0. That's like our B, right? Either A equals 0 or B equals 0, but one of them has to be 0. All right. So we're layering on a little bit more algebra. All that factoring, we're bringing it back to expand the types of solutions or equations that we can solve, okay? So let's see what we get. I bet you folks can tell me this one. The angles in the unit circle where the y value is 0. What do we get for that? Zero and pi. Okay, so we're gonna take Michelle's answers here, 0 and pi, because check out this little thing. You see where we have a parentheses here? That means we're not including 2 pi in our answer. So it's like we're going from 0 to like 359.999999999 degrees. Okay, so we're going to go with 0 and pi, though, Fia, your answer would be correct in like a general solution. Okay, so 0 and pi, I only have one x. It's not like 2x, so I don't have to do any of the stuff I did in problem 6 and 7. Okay, now how do I get sine x isolated in the second part? -1 divided by 2 sine x equals -1/2. All right, I bet you can give me these answers too. How do we find the angles that have a y value of -1/2? Where are those angles? (11 pi over 6), I love it. And 7 pi over 6, beautiful. Okay, excellent, excellent. All right, so the tricky part to this problem is the factoring part. But once you've factored it, it's very much like questions 1 through 4, okay? Now, before we write our general solutions, let's draw a picture because I don't want to write more general solutions than I have to. So if any of these angles are exactly halfway around that unit circle, I can actually collapse those two solutions and write them as one, okay? But if they're not exactly halfway around, then I have to write them as separate solutions, okay? So let's draw all our solutions on a unit circle so we can get that visual. Whoa. Ah, okay. So I've got a 0. Nope. I've got a 0. I've got a pi. Ooh, those are halfway around the unit circle exactly. So those two solutions I can actually write as one solution, right? Because it's the special case where they're exactly separated by pi. But let's see about the other solutions. 7 pi over 6 is like here. Okay, so that's this one. And 11 pi over 6 is like here. Are the purple and the orange separated by exactly half of a circle? No, they're not, right? So we're going to have to write the purple one and the orange one as separate solutions, okay? But the green and the pink one, because they are exactly halfway around the unit circle, we can write those as a single solution, okay? So x can equal k 0 plus k pi, where k is an integer. This one is the pink solution and the green solution together in one. Okay, because now I'm just stopping every half rotation. Okay, but the other two, because there's not such a clear-cut pattern, I have to write them as one solution and then the other. So purple and orange. Okay. Does that kind of make sense there, folks? Why we're able to write two of them in the same solution, but the other two we can't? Yeah, I have one yes. Give folks another moment to ask any questions. Yeah, so that's a good question. This could actually be pi k. I don't know why I wrote it as k pi. Yeah, when we're multiplying, the order doesn't actually matter. So we could do like k2 pi or k pi. Those would actually mean the same thing. Okay. Well, that's the whole purpose of the general solutions, is to make sure you hit the angle every time. So that's why we kind of have to keep them separate. Yeah, yeah. We want to write something that actually works all of the time. Okay. All right, so let's do this. Let's take another break. All right, we've got 1, 2, 3, 4, 5 equations left to solve, okay? But I think we've done a lot of big thinking in the last few questions, so it seems like a good time to kind of regroup and think about where you are, okay, and what questions might come up. So I'm gonna, before I forget, all right, so we've got 5 more examples to take a look at. We're going to do one more that does the factoring, okay? So one more chance to kind of practice the factoring and whether we can collapse things into a single solution or not. And then we'll finish up today with what it looks like when we employ some of the identities that we've learned. I know, super excited about this, but when we employ some of the identities that we've learned to help make the equation that we have into a form that we already know how to solve, okay? So I'm gonna go ahead and share my screen. All right, here we go, folks. So example 9, all right? So when we look at example 9, this should be a situation where you're like, yes, we're gonna factor because we have the squared, all right? And then as soon as you see the squared, you're also like, ooh, let me double check and make sure I moved everything to one side and it is equal to 0, right? We have to make sure that part is there. So it's already fulfilling both of those, so we can jump right into factoring, okay? Now, if this is like too much for your brain to sort of wrap itself around, you could definitely do something like this, like 2y squared minus 3y plus 1 equals 0, right? That's the same form as when we have 2 sine squared minus 3 sine plus 1. Okay, but either way, we're going to use what we know about factoring, okay? And so when we factor this, we should end up with 2 sine x and then minus 1 and sine x minus 1 equals 0, okay? I don't want to spend too much time on how we factor, but I would really encourage you to practice that because it's not a piece that goes away, and I don't want you to get turned away from higher level math because of factoring. Like, that seems silly, okay? So once we factored it, we got it equal to 0. All that means is we're going to set each piece equal to 0, see what we get. All right, in that first one, we'll get sine x equals 1/2. And in the second one, we'll get sine x equals 1, okay? And so now we're just thinking about which angles around the unit circle fulfill those requirements, all right? And so for the first one, we should get x equals pi over 6 and 5 pi over 6, all right? And doing a quick visual check on your unit circle, are these two separated by exactly pi? Like, are they exactly halfway around the unit circle from each other? No, they're not. So we're going to need different solutions for those when we go to the general solutions, okay? So we're going to have one that we'll write as a general solution. We'll have another one that we're going to add 2 pi k to. And then let's finish solving this last piece, sine x equals 1. Well, that happens when x is pi over 2, okay? And this one also does not is not exactly halfway across the unit circle from any of the other ones. So what that means is we'll have 3 general solutions, okay? So we get x equals pi over 6 plus 2 pi k, where k is an element of the integers, okay? That corresponds to the pink one. We've got x equals 5 pi over 6 plus multiple times around the unit circle, where k is an integer. And we've got the last one where x equals pi over 2 plus rotations around the unit circle. And that's that, okay? So definitely more work than the linear ones, but mostly just because we have to remember how to factor, okay? But once we've got the factoring piece down, we set each side, we set it equal to 0, and then we just add 2 pi k to get our general solutions, okay? Are there any questions about example 9? Well, if you think of any questions, feel free to type those in the chat. But for right now, we're going to move on to trig equations with identities. All right, so this is the case where we need to start thinking about what identities might we need. All right, so if you have your unit circle, that's great. But if you have your list of all your identities, that's probably even better right now, okay? If you haven't made that yet, I would really encourage you to make a list of those identities with all their names and stuff for that reference sheet, okay? All right, so let's take a look at example number 10 here, okay? So what makes this question different than, say, question number 9? Right? Because at first glance, you might think that they're exactly the same. Okay. So in example 9, everything was sine, right? But let's look more carefully at example 10. I've got sine and I have cosine. Okay. That's like trying to factor when you have something like this, 2y squared minus x minus 1 equals 0. Right? You've got 2 different variables here. And the way we know how to factor, we only know how to do it with one variable, okay? So here's where the other identities are helpful, right? Now, if I could rewrite this, okay, this is the important part. If I could rewrite this with only sines or only cosines, I'd be good to go. Because then it would look exactly like number 9 or number 8. Good to go. So what ideas do folks have about how I can turn this into an equation with only sine or only cosine? Okay, this is the key here. So sine squared minus 1. Okay, are you thinking about this identity? Yeah, okay, so not the double angle one. That's not what she's saying. She's looking for that Pythagorean identity. Okay, so what could you write instead of sine squared? Like, what does this equal? How do we get from cosine squared plus sine squared equals 1 to, yeah, okay, there we go, there we go. So I'm just going to subtract the cosine squared to both sides, okay? So 1 minus cosine squared. Okay. Well, check this out, folks. Instead of writing sine squared x, we could write 1 minus cosine squared x, okay? We can just do a simple substitution here. We've got 2. Instead of sine squared, I'm going to write 1 minus cosine squared. And then I'm going to keep the rest of my equation the way it is. Minus cosine x minus 1 equals 0. Okay. Ethan, you figure that out? Okay. So if you were annotating your notes, you could say that you use the Pythagorean identity here. Okay. Yes, exactly. You were on the right path. You just switched the wrong thing. Okay. So all we did was we used the Pythagorean identity. We solved for one of the variables, and then we were able to make a substitution. Now, how did we know to solve for sine squared? Well, our whole goal was to get it so that we have only sine or only cosine. That was the goal. Okay. So if you're like, I don't really understand how people are making decisions, you have to do the work in the first place to figure out what the goal is. Okay. You have to understand that first step. Otherwise, you're just following someone else's work. All right. Which I know no one is going to do on this test, which is follow someone else's work or look up solutions online. Okay. I will know if you looked up solutions online. I'm telling you right now, I will know. Okay. So we're annotating this so we remember like why we did this. We're doing this so that we can get in terms of cosine. Okay. Now we just need to do a little bit of work, and then I bet we're going to be able to make it look pretty much like example 9. Okay. So I'm going to distribute. I'm going to do 2 minus 2 cosine squared x minus cosine x minus 1 equals 0. Okay. Now, I like to factor with everything, like with the squared term positive. So I'm going to move everything to the right-hand side. Okay. So that means I'm going to get 2 cosine squared x plus cosine x minus 1. Okay, because 2 minus 1 is 1, but when I move it to the other side, I get a negative 1. Okay. Now, well, this basically looks like what we had for example 9, right? We use the identity to make it into a quadratic that we know how to solve. Okay. So now we're going to factor, we're going to set each piece equal to 0, and we're going to see if we can combine any of these solutions into a single solution for the general part, okay? so here we go. Factoring, we'll get 2 cosine x minus 1, and then cosine x plus 1. We're going to set each part equal to 0, because that is the beauty of having it equal 0. We can't do it if it's not equal to 0. We'll get cosine x equals 1/2, and we'll get cosine x equals -1. Okay. We check our unit circle, we see where these things are true. We'll get pi over 3, 5 pi over 3, and x equals pi. Okay. So I know I went through that last part kind of fast. I'm going to pause here and let you kind of take a look at that, write down what you need to write down, see what kind of questions you're coming up with about where things went or where things came from.
For some reason, I'm blanking on this right now. But could you please explain how you got, like, when you factored for those two quantities, like how you did that?
If you have questions about factoring, I would maybe stop by office hours.
Okay, cool.
But for right now, if you can foil it back into where it came from, then that would be helpful.
Oh, okay. Never mind. I think I got it. Thank you.
All right. So from here, the general solutions, we can do a quick check, but I don't think any of these are collapsible into exactly halfway around the unit circle. So we'll have to write out each one as an individual solution or set of solutions. Okay. So the thing that makes it a little bit more than example 9 and example 8 is just you have to get it into that factorable form in the first place, okay? So we use that Pythagorean identity there to make that switch. All right. Of course, we have so many identities, so we got to do a few of the other cases too and see what comes up, okay? But this is why it's helpful to have a whole sheet in front of you about all the identities, right? Because when we look at number 11, we should 100% not be thinking Pythagorean identity. Which identities might be useful in example 11? Don't just say a random answer. Think about what this looks the most like, okay? What does it look the most like? And that is a mistake you do not want to make on the exam. It is not that. All right, but I bet that's going to be the number one mistake I see. Well, why is she so close? Cosine difference. Okay? Yeah. Yeah. Okay. The cosine one, it is easy to get confused, all right? That's why when you write that reference sheet, you make sure that everything is the way it's supposed to be, all right? So the sine, plus is plus, minus is minus, but the cosine one, that one is the opposite. Remember when we did the notes that day, we talked about how with quadratic formula, we've seen like the plus minus symbol, right? But then for the cosine, we used the minus plus symbol. Okay, so we want to be really careful about those small details. Okay. All right, so we do in fact have the cosine difference formula here, or identity. And so let's write that out. We've got cosine of x cosine of 2x minus sine of x, plus sine of x sine of 2x equals cosine of x minus 2x, okay? So we're literally pulling the equation straight from there. Now, I'm really glad that no one, at least out loud, said the double angle formula, okay? I can see why people would say double angle. But a lot of the cases we're going to see here are like almost short of waving a sign that says use the cosine difference. They're basically giving you the formula, okay? I'm sure. All right, so you could, but you're going to be really upset about it because it's not going to get better faster. You'll in fact end up with a more complicated equation, okay? So here's our identity. We're able to turn the left-hand side of that equation to be cosine of, let's see, x minus 2x is negative x, okay? So we have to use one more identity. What is that other identity? Exactly. We're looking that it's even, okay? And we should be like on the lookout for that. We see the minus with the x and we're like, oh, is it even or odd? That should be a question we're asking ourselves, okay? So since this is even, that means we can say cosine of x is root 3 over 2. And now this looks pretty much like question 1 or 2, okay? Yes, it is. It is still root 3 over 2, okay? All right, well, where are all the places where this is true? We've got pi over 6, and we've got 11 pi over 6, right? And are they separated like exactly by pi? Well, I sure wish, then I would only need to write one solution, but they're not, so I have to write each one plus 2 pi k separately. Okay, so we needed 2 identities here in order to our equation into a form that was either like a linear one or a quadratic one. Okay. All right. Any questions on example 11? All right, so let's go back to number 10 for a moment and just kind of think strategy here, right? So we knew going into number 10 that we could solve a quadratic trig equation. And this one was like almost quadratic, but the problem was there was like sines and cosines mixed together, okay? In these cases, the Pythagorean identities tend to be pretty useful so that you can get them all to be sine or all to be cosine, and then you can factor. Okay, so I'll give you a moment to write that down. If you're like, I don't know how to make these decisions, I'm trying to tell you here, okay? If you see like a quadratic-y situation, but you don't have the same variables, you can usually make them into the same by using the Pythagorean identity. That's sort of one case, okay? Yes, if they were exactly separated by pi, then you could write the one solution plus pi k, and that would be all right. Okay. All right. Second flavor is there might be one that asks you to use the cosine, like the sum or difference formulas, right? So we want to know those, and we want to be able to match those accurately. And Thea, I apologize for putting you on the spot like that. I just know that you were not the only person who would have said that. Okay, so I wanted that to be sort of a learning moment, but I hope that was okay. So when we look at these, we want to match the equation super, super carefully. We want to make sure everything's in the right place. We're not going to panic if we get like a negative x there, because as soon as we see a negative x, then we're thinking like, all right, well, is it even? Is it odd? Like that's a very typical process to think through, okay? So then there's sort of two more flavors that I want us to be aware of, okay? So we've got example 12 here, which has cosine of 2 theta equals cosine theta, all right? And then example 13, we have sine of 2 theta equals negative sine of theta. So when we take a look at number 12, I feel like no one's going to want to answer now because I might blow up your spot. But when we look at number 12, what identity or identities are we thinking about? The double angle. Okay. So I see a 2 theta here, right? So I'm thinking double angle. And actually, if we look ahead to 13, we see a 2 theta as well. Okay. Now, I'm going to go back for a moment because we saw 2 theta earlier. We saw 2 theta in example 7. Was there any other trig function in example 7, or it was just the cosine of 2 theta? It was just the cosine of 2 theta, right? And then we had like numbers. Okay. If it's only a cosine of 2 theta or a sine of 2 theta, then you can approach it like we did for number 7. Just get everything to one side, set it equal to 0, okay? But when we look at 12 and 13, okay? So I forget who said this. I think it might have been Edward, like double angle. When you're looking at 12 and you're looking at 13, here's how you know that you're probably going to use a double angle. You're probably going to use a double angle because you don't have other numbers here. You have another function. Okay. So when you have another function, you want to use the double angle. Right? But when it's just a cosine of 2 theta with some numbers, or just a sine of 2 theta and some numbers, you probably don't want to use the double angle. Okay. All right. So I wrote number 12 first because what are the other ways that we can say cosine of 2 theta? Right? What are the identities that we have for cosine of 2 theta? I can't stop reading tacos in the middle of that, Richard. Everybody else see tacos in there? Okay, so you, first of all, yeah, so it's the sine double angle one, but also I can't get rid of that tacos. Okay, so let's go back and see what other identities. All right, so we've got cosine squared minus sine squared. That's one variation. We've got, what other variations we have? 1 minus 1 minus 2 sine squared theta. Yeah, I buy that. There's one more version. Good. 2 cosine squared theta minus 1. Okay. Now, I forget who asked it. I feel like it was David. I could be wrong, but someone was like, why do we have so many? And how do we know when to use which one? Okay. So now this is actually our chance to kind of think through which one might be better here. okay? So I could say this, cosine squared theta minus sine squared theta equals cosine theta. I could make that substitution. I could also do this, 1 minus 2 sine squared theta equals cosine theta. Or I could do this, 2 cosine squared theta minus 1 equals cosine theta. Right? All three of those would mathematically be accurate. But one of them is better than all the rest of them. As in, one of them will make your life way easier than the rest of them. Anybody have any instincts around this one? Ooh, yes, for the redemption. 2 cosine squared minus 1. Okay, your reasoning behind that. Why this last one? Because everything is in cosine, right? Well, that's sort of similar to the logic we did up here for number 10, right? We want everything to be one trig function, all sines or all cosines, but just all of the same, right? So when we think about that, all three of these mathematically accurate, but well, this brings the sine squared into the picture. This one also brings the sine squared into the picture. But the last one gives me a quadratic with only cosine, okay? And so what we can do from there, bring everything to one side, set it equal to 0, and factor, okay? And we factor minus and plus, okay? And then we're going to set each piece equal to 0. So we've got 2 cosine theta plus 1 equals 0, and cosine theta minus 1 equals 0. Or cosine theta equals negative 1/2, or cosine theta equals 1. And we think about what makes those true. We've got 2 pi over 3, 4 pi over 3, and we also have 0. Okay. I'll give you a moment to write all those down. I know I wrote those pretty quickly, okay? But just kind of as a reflection of like, we're going to be doing questions that are layered like this in calculus. And what I mean is they're not all going to be trig equations. I don't mean that. But I mean like we're going to use some new skills, right? So the new skills is like this part. That's the new part, right? To help us get to something that we know, and then the rest of the problem, a lot of it is going to be algebra, okay? So when we get to calculus, we're really thinking about how good are these fundamental skills, right? How good are we with factoring? How well do we know our unit circle? Those things are going to come up again and again. So if you're not there yet, that's okay. You have until February 1st to get there. Okay, but this is kind of like the way we're going to be going through some of those questions, which is here's the new stuff. Now let's move through that old stuff, use all the tools we already have to answer that question, okay? Are any of these angles exactly halfway around the unit circle from any of the other ones? No. So since none of them are halfway around, we have to write them all out. Here's one. Here's the other. And the third one. Okay, so none of them are halfway around, so we can't collapse any of them. We just need to go ahead and write them out separately, okay? All right. All right, we got one more example here. All right, sine 2 theta equals negative sine theta. And so what we're going to do is actually very similar to number 12. We're going to think double angle identity, because it's not sine 2 theta and a bunch of other numbers. It's sine 2 theta and another function. Okay. Now we'll go back to the sine double angle, which means that I can replace sine 2 theta with 2 sine theta cosine theta. And that's the only one I have to choose from. I still can't stop seeing the tacos. Now they're high, all capital. Okay, so now we have this, all right? What are people's thoughts on how we should solve this? Right? How do we solve this? Okay, I'll give you a hint on what we don't do, all right? We do not divide the signs away from both sides. So if you did that, just erase it, don't do it, okay? Yep, we're gonna move everything to one side, set it equal to 0, okay? So even though this is not a quadratic in the sense that I have like sine squared, okay? It's sort of quadratic in the sense that I have like something times something else of the same family of functions, okay? But the nice thing about, yeah, we already did that double angle. The nice thing about moving everything to one side and setting it equal to 0 is we can still factor here, right? It's not a quadratic in that sense, but we can factor out the sign because we actually have a greatest common factor. Okay, so don't panic every time someone says factor, right? Think about it. Sometimes we just need a greatest common factor. And I know you folks can do that. I know you can find a greatest common factor. So you kind of got to trust in yourself a little bit, right? Find that greatest common factor. And oh, shoot, it's equal to 0. So the first part can equal 0 or the second part can equal 0, right? That's the beauty of the 0. All right. Now we use our unit circle. We get these solutions. We get these solutions. Okay. Now I know I didn't write out every step here, so let me give you a moment to make sure you connected the dots between what I wrote down first and what I wrote down at the end. Okay. Now from here, I see that I have 4 solutions. Why wouldn't it be 3 sine theta? Because this is multiplication. It's not a like term. You can't combine those. Yeah, I know. I know. It's like so many of these rules that we know, like we can't combine things if they're not like terms, but sometimes they don't look like terms because it has like a, so many other letters. Okay. So the good news here, though, is these two, the 0 and the pi, I can collapse those into a single solution. because they're separated by pi. So I could say theta equals 0 plus pi k for 1. And then the other two, unfortunately, are not separated by a half circle. So I have to write those all out. Okay. Yes, that is not true. Sine 2t is not the same term as sine t. Okay. The 2t has been signed and the t has been signed. So you can't combine them. All right, I know that was a very jam-packed day, but I did want to take some time to clarify a lot of the questions that folks had along the way, because I think that was actually, I hope it was really important and valuable for you, okay? So as you are looking over quiz 11 is the last quiz you have due before Thanksgiving break, okay? So as far as deliverables from you, make sure to check over the announcements to see what you have to turn in, but you've got quiz 11, you do have an exam this week, okay? And then that math and writing assignment number 6 on Sunday. So make sure you've got all those done. Wednesday is your time to do whatever you choose. It might be studying for the exam. It might be looking at the stuff for chapter 8. I'll leave that up to you, but make sure that you have looked over that chapter 8 first 2 sections at some point before quiz 12 is due, which is after Thanksgiving break. Okay. All right, folks, I'm gonna